Let's talk about how the Laplace transform is similar to and different than the Fourier transform. We'll start off talking about the Laplace transform that we studied in the beginning of the year. The mathematical definition is that it's the integral from just before 0 to infinity of the function times e to the minus st dt. And compare that to the Fourier transform. Here we're going to integrate over all time, so it will pick up everything that our function does, including the left side of the function before time equals 0. We're going to multiply it by e to the minus j omega t. The type of functions that lend themselves towards having Laplace transforms are functions that are multiplied by u of t. In other words, right-sided functions. Functions that start off as 0 because of that u of t, and then start to do something after time equals 0. And that's because, this is our first point, this is our second point, and that's because this integral doesn't pick up what the function does before time equals 0. Compare that with a Fourier transform that works with two-sided signals. Signals that can do something on either side of the 0 point. Here's our 0 point for the Laplace transform. So of course the Fourier transform can work with right-sided signals, or left-sided signals, or two-sided signals, whereas the Laplace transform will only pick up the action of what a function does after time equals 0. You find the Laplace transform prevalent in controls courses. It shows transients that are caused by the startup of a u of t. So it shows the transients caused in a step function. The Fourier transform is more common in communications courses. Let me just point out the bullets on these sides. It provides intuition about the frequency content of signals. Okay, so in some ways they seem very similar, in some ways they seem very different, but if you take a look at the integral definition, if you replace that s with a j omega, then with the exception of this lower boundary, it looks the same. So, aren't they the same? But with s equaling j omega, s in the Laplace domain, going to j omega in the Fourier domain. And the answer is it varies. Yes, for circuit components. So as an example, a capacitor has an impedance of 1 over Sc in the frequency domain for Laplace, or 1 over j omega c in Fourier. The Laplace transform of an inductor looks like SL. For a Fourier, in the Fourier transform, the inductor looks like it has a j omega L impedance. Yes, for most right-sided signals. So as an example, an impulse in the time domain has a Laplace transform of 1 and a Fourier transform of 1. Similarly, an e to the minus 2t u of t has a Laplace transform of 1 over s plus 2, or a Fourier transform of 1 over j omega plus 2. However, they are different for all left-sided signals and for some right-sided ones, specifically u of t. So let's go over these. Here's our u of t. This is the only right-sided function that I'm aware of that has a different Laplace and Fourier transform. Its Laplace transform is 1 over s, but its Fourier transform is 1 over j omega, which looks the same, but then multiplied by a impulse. A two-sided signal, like 1, something that's 1 everywhere, well, in the Laplace domain, it only picks up the right side of that since it starts integrating at 0, so therefore it has the exact same Laplace transform as u of t, but it has a very different Fourier transform. And then there are some signals like cosine of 2t, which has a Laplace transform of s over s squared plus 4, but a Fourier transform. And of course, this is the same Laplace transform as if it was cosine of 2t times u of t. In other words, the inverse transform of this is not cosine of 2t, but cosine of 2t times u of t. However, it does have a unique Fourier transform, which are two impulses in the frequency domain centered around omega equals positive 2 rads per second and negative 2 rads per second. Let's look into how the Fourier transform allows us to modulate multiple signals onto the same communications line at the same time.